This control circuit here is controlling the Boost PFC. Here we use a cascade control, which means that the voltage control gives out a current reference, which goes into the current control, which gives out the input for the PFC. And here we use a PWM in order to convert from the duty cycle that we want into the PWM signal that we need for the MOSFET. First, we're going to look at a current controller. So it consists of a PI controller and a feed forward. So the reason why we have a feed forward is so the delta D can be as small as possible. This will make the system more stable and accurate. In order to understand why we do this, we first need to understand the PFC. Now, when controlling the PFC, we're actually only looking at the boost converter. So we want to control the output voltage and also the current going through the inductor. Vin is actually just a disturbance, and the duty cycle is the input, which means that it is the parameter that we change in order to get the results that we want. So we first want to look at the gain of the boost converter. So the gain could be written as VO over VI, which is equal to 1 minus D. 1 over 1 minus D. Now, as you see from the controller circuit, we want to control the D, or we want to find D. So if we solve this for D, we get 1 minus VI over VO. Now, this should be the equilibrium point for the duty cycle, which means that if the current going through the inductor is equal to the reference current, then the duty cycle should be this. You can also see that in the controller, because we actually feed forward this part. So if we want to change the current, we can just move the duty cycle out from the equilibrium point. So we can just add a delta D. Now, if we want to find the change of delta, we need to look at what happens when, for example, the duty cycle increases. Now, when the duty cycle is 0, there's no current going through the MOSFET. And the output voltage is larger than the input voltage, which means that the current in the inductor has a negative. No, the voltage over the inductor is negative, which means that the current is decreasing. Now, if the duty cycle was 1, this MOSFET would always be open, which means that the voltage over the inductor here would be equal to VI, which is positive, which means that the current is increasing. Now, if we go from the duty cycle of 0 to 1, the current would increase. Now, this means that when the duty cycle is increasing, the change of current is also increasing. No, the current is also increasing. So we can actually write the change of duty cycle as a constant K, which is positive, multiplied by the change of current. Now the change of current is actually the error, which is the reference current minus the current in the inductor. And this constant K is the PI controller. So it's not actually constant. It's this one. If the inductor current is lower than the reference current, we need to increase the current. And the gain in the PI controller is always positive, which means that we get an increase in the duty cycle. And the increase in the duty cycle will make the current increase again. Now, this is the equation we get for the duty cycle if we just put this one into this one. And as you can see, this controller here is exactly this equation, where the K here is a PI controller. So it's not constant, it has a integral term as well. Now we want to look at the voltage control. So we take in the output voltage and we want to find a reference current. Here we have a PI controller with a saturation, which means that we also need a anti-windup. And here we have a feed forward, and we also have a oscillator. The oscillator is actually going from a value to a sinusoidal waveform. Not actually sinusoidal, but the absolute value of a sinusoidal. And we also need a oscillator, and it is to get the waveform that we want for the reference current. So if we assume that we have a power factor of 1, so PF is equal to 1, then now we need to remember that this is a PFC, so we assume that the power factor at the input, no, the source, is equal to 1. So PF is equal to 1, and therefore the waveform of the voltage source is equal to the waveform of the current source, which means that they are proportional. Now the rectifier just takes the absolute value of the current and the voltage. So we could say that the input voltage is equal to a constant multiplied by the input current, which is the inductor current. So now we know the waveform of the inductor current here. So we can actually just find the peak and multiply it by the waveform. This is just a quick example of how you can implement the oscillator. So you have the input voltage here, and then you divide by the input voltage, the peak value of the input voltage, just to get the same waveform with amplitude of 1. And then you multiply it by the peak value of the current reference. Now we just need to find the equilibrium point of the reference current, or the peak of the reference current. And it is what we want to feed forward into the controller. So it's this. So we start off with a power balance. So we have the power going in is equal to the power going out, assuming that we have no losses. Now this is equal to the voltage going in multiplied by the current going in, which is equal to the inductor current. And it is again equal to the voltage going out multiplied by the current going out. So we want to find the peak current of the inductor current. So this is equal to VI over 1 over the square root of 2 of IL. Now if we solve, oh, I just forgot the hat. Now if we solve this for the peak current, we get the square root of 2 multiplied by VO multiplied by IO over VI. It doesn't really matter how you write this expression. You can also have the P out instead of VO IO, or VO squared over R. So this would now be the equilibrium point for the peak reference current. And if we want to increase the reference current, we could add a change of reference current, or change of inductor current. Now we want to find out what happens with the output voltage when the inductor current, or the peak value of the inductor current, increases. When the MOSFET is off, the inductor current is equal to the current flowing through the output, which means that when you increase the inductor current, the output voltage will also increase. The change of voltage, or output voltage, is therefore larger than 0. Which means that we can do the same trick as for the current control. The change of inductor current is equal to a constant, a positive constant, multiplied by the change of output voltage. And now this is the PI controller, and this is the error. If we now put this one equation here into this one, we get this. Assuming that the error here is the voltage reference minus the output voltage. And this constant K here is a PI controller. Now we are finding the peak reference current, which means that the peak reference current can't be lower than 0. And that is exactly why we need this saturation here. Now, if this output voltage is a lot larger than the reference voltage, this change of current could become so small that this reference current could be less than 0, which doesn't make sense. Therefore, we want to limit the change of current so it can't become lower than minus whatever we feed forward. Because if it is lower than minus this expression, this would become less than 0. We don't need to have a upper limit for the saturation, so we can just set it to infinity. Now, if you want to get the complete control circuit, you just put the voltage control next to the current control. So you have this cascade control as I showed you in the beginning. So just to recap a little bit, this is the voltage control, and then we have a oscillator to get the reference current, and then we have the current control to get the duty cycle, and then we have a PWM to get the input signal for the MOSFET that goes into the PFC.